So now, still in section 3.4, we're going to take a look at something called the second derivative test. And this is a different way that we can find relative extrema. We're about to look at the second derivative test for relative extrema, relative maximums and minimums. And that might sound kind of wrong to you because you know that we can use the first derivative to figure out where our function has a relative max or relative min, and our second derivative is used to figure out things about concavity and points of inflection. But there's another way that we can use the second derivative to determine where our original function f of x has a relative max and a relative min. And this is called our second derivative test. And this second derivative test says the following. If f prime of c equals 0, so if we have a particular x value and it makes our first derivative equal 0, then we're going to go and we're going to plug that value into our second derivative. If f double prime of c is positive, then f has a something at the point c comma f of c. If my first derivative is 0, then if my second derivative is positive, f has a something at c comma f of c. Well, let's think about this for a moment. If my second derivative is positive, from the last video, that tells us what are we? Are we increasing? Are we decreasing? Are we concave up? Or are we concave down? Second derivative being positive means I'm concave up. So we should have something that takes on a shape like that. Now, if I'm concave up, and if my first derivative is 0, where along something concave up must we be? We must be right over there, at our relative minimum. If my first derivative is 0, then if my second derivative is positive, which means I'm a concave up, f has a relative minimum at the point c comma f of c. Likewise, if f double prime of c is less than 0, then f has a something at c comma f of c. If the second derivative is less than 0, what does that mean about our original function? Is our original function f increasing, decreasing, concave up, or concave down? Hopefully you said concave down. I've got something that kind of looks like that. And where on something concave down is my first derivative? 0? Right over there, at our relative max. If my first derivative is 0, then if my second derivative is positive there, I have a relative minimum. And if my second derivative is negative there, I have a relative maximum. There is one other case. If at the place where the first derivative is 0, the second derivative is also 0, then we actually can't tell. We might have a relative max, we might have a relative min, we might have nothing special. We're just going to say, then the test fails. And we have to use probably our first derivative test in our number line to figure out for sure if there's a relative max or a relative min there. Take a moment, copy this down, and then I have 2 examples I'm going to show you. For our first example, we are going to use the second derivative test to find and classify the relative extrema for the function f of x equals negative 3x to the fifth plus 5x to the third. Take a moment, get that copied down. Oh, sorry, one other thing I want to add into the direction here. We are going to justify your answer. Okay, well, if we're doing this according to our second derivative test, we first have to find places where the first derivative equals 0. Take a moment, get your first derivative. Okay, so let's see here. My first derivative is f prime of x equals negative 15x to the fourth plus 15x squared. And then I need to find where this first derivative is going to equal 0. How about you take a moment, do some factoring, find your critical values, find what makes your first derivative equal 0, and send those into Edpuzzle. Okay, let's see. I'm going to take out a negative 15x squared. I'm left with an x squared minus 1. You know, I'm just going to keep factoring this because I can. I'm going to get negative 15x squared times x minus 1, x plus 1. I'm getting 3 critical values here. I've got critical values at x equals 0, negative 1, and positive 1. That's how we start this problem. We find our critical values. Now, I'm going to need to plug these 3 x values into my second derivative to see if I'm concave up and I have a relative min, concave down and I have a relative max, or second derivative is 0 and then I can't really tell much. Take a moment, take this version of your first derivative, and calculate your second derivative. Let's see, f double prime of x equals negative 60 x cubed plus 30x, I believe. We're now going to go plug these values into our second derivative. So I'm going to go and I'm going to do f double prime of negative 1. And that's going to give me negative 60 times negative 1 cubed plus 30 times negative 1. Okay, well, negative 1 cubed is negative 1, times negative 60 is positive 60, minus 30. I'm getting a second derivative of positive 30. Now, it's nice that it's positive 30, but I don't even really care about the 30 part. I just care about the fact that it's positive. Because my second derivative is positive, what does that mean about the original function at x equals negative 1? Is my original function increasing, decreasing, concave up, or concave down? Because my second derivative is positive, I'm concave up. Since my first derivative is 0, that means I have a relative minimum. At negative 1 comma something. How do we find the y-coordinates? Is it just going to be 30? Or is that not going to work? Where does the y-coordinate come from? We need to go and plug back into our original function. So 1 comma, whatever f of negative 1 is, I think that's going to be negative 3 times negative 1 to the fifth plus 5 times negative 1 cubed. That is, let's see, negative 1 to the fifth is negative 1 times negative 3 is 3 minus 5, I'm thinking negative 2. And now our directions that justify our answer, here's what we need to say for our justification. By our second derivative test, there's a relative minimum there because f single prime of negative 1 equals 0, and f double prime of negative 1 is positive. And that's what your second derivative test justification is going to look like. I'd like you right now to go plug 1 into your second derivative, and then tell me what we have at x equals 1 and give me a justification as well. So second derivative is negative 30, but I really just care about the fact that it's negative. That means I'm concave down. And where is my first derivative 0 on something concave down? At the relative max. So there is a relative max at 1, comma, I'll figure that out in a moment. I might as well get my justification in there. Because f prime of 1 equals 0, and f double prime of 1 is negative. Okay, 1 comma what? Well, let's see. I'm going to go plug into the original. Negative 3 times 1 to the 5th plus 5 times 1 to the 3rd. Negative 3 plus 5, I'm getting 2. So there's a relative maximum at 1 comma 2. Why? Because f prime of 1 is 0 and f double prime of 1 is negative. Hopefully that's what you sent into Edpuzzle. One more. Please go find f double prime of 0 and tell me what we have there. You're going to say something like relative min or relative max at 0 comma whatever because, and give me the justification there. Negative 60 times 0 to the 5th plus 5 times 0 to the 3rd. That's 0, which means I don't actually know anything. The test fails. I could have a relative max or a relative min there, or neither. I don't really know because my test fails. The only way I could do this for real is by using my first derivative test, making the number lines, and see if the number line changes, if f prime changes from positive to negative or negative to positive at x equals 0. Second derivative test didn't get me there. So, you might be wondering why we actually need the second derivative test. Could I have done this original problem using things we already know, doing my first derivative, making the number lines, and testing the regions? Absolutely. Might this have been a little bit easier because I didn't have to go to the number lines? Yeah, it might have been. But there's no real advantage, I don't think, in this problem to using the second derivative test over the first derivative test. And actually, we did see a disadvantage. I don't really know what's going on at x equals 0. Let me show you one other example where there's going to be no way around using the second derivative test. Last example for this video. We are going to consider the curve given by x squared plus 4y squared equals 7 plus 3xy with, I'm going to give you dy dx, with a derivative of 3y minus 2x over 8y minus 3x. Whoops, you can't see anything I'm doing. Sorry about that. I'll make the video pause in a moment once I'm done writing everything. I want to figure out, is 3 comma 2 a relative max, relative min, or neither? And of course, I'm going to justify your answer. I'm going to make Edpuzzle pause for a moment, get that copy down, and then we've got to figure out what's going on with this. Okay, well, there is no way I can make a number line for something like this and test the regions. My first derivative test back from section 3.3 is not going to be helpful here. But I think I can use my second derivative test to figure out what's going on at 3 comma 2. Remember, the first part of my second derivative test is to plug 3 comma 2, my point, into my first derivative to see if that first derivative equals 0. Take a moment. Go plug 3 comma 2 into dy dx and tell me what your first derivative equals. 3 times 2 minus 2 times 0, that's looking good. over 8 times 2 minus 3 times 3. That's 6 minus 6 over 16 minus 9. That's 0 over 7. That's 0. That's good. I passed my first part of the second derivative test. If the first derivative wasn't 0, you could say right away that you will have neither at 3 comma 2. Now, we need to plug 3 comma 2 into the second derivative. Well, let's see what we can do for our second derivative over here. D squared y dx squared equals low 8y minus 3x. D high is going to be 3 dy dx minus 2 minus, how about you take a moment, the video is going to pause, see if you can do your, let's see, I did low d high, see if you can do your high d low, draw the line square below, and then stop. We'll do the plugging in together. Low d high minus high 3y minus 2x. D low is 8 dy dx minus 3. Draw the line and square below over 8y minus 3x in parentheses squared. Now, I want to see what happens when I plug into this. I want to go plug in my 3 comma 2. So I'm going to get 8 times 2 minus 3 times 3 times 3, oh, wait a minute. I need to plug in dy dx. Actually, I don't have to plug in my formula. I already know at 3 comma 2, what's the value of dy dx? We already found that over here. Dy dx is going to equal 0. So I'm going to say times 0 minus 2 minus 3 times 2 minus 2 times 3 times 8 times 0 minus 3 all over 8 times 2 minus 3 times 3 squared. How about you take a moment, clean that up, and tell me what the second derivative is at 3 comma 2. Okay, 16 minus 9 gives me 7 times 0 minus 2 is times negative 2 minus 0 times negative 3, that's not going to matter, it's just 0, over 16 minus 9 squared over 7 squared. So this is negative 14 over 7 squared. That's negative 14 over 49. That's negative 2/7. And I do want that number. But now I think I can make a conclusion about what's going on at 3 comma 2. What do I have at 3 comma 2? A relative max or a relative min? Second derivative is negative. That means I'm concave down. That means I've got a relative max. There is a relative max at 3 comma 2. Why? Because my first derivative, dy dx, at 3 comma 2 equals 0. And my second derivative, d squared y dx squared, at 3 comma 2 is negative. Anytime you're told in the directions to use the second derivative test, this is sort of the work I'm looking for, or anytime you're just asked about relative maxes, relative mins, and there's no way you can do a number line and use our first derivative test, like if you have an implicit function, second derivative test will be the way to go.